let the particle move in this particular path. Particle, since body means again its parts will come, no? So that's why I'm choosing a particle. So initially, so let it be at a position. I'll define its position. Let me choose some other color. So initially, let me define its position. So let at t equal to 0, the position of particle is defined by r of t. What is r of t? It's a position vector. It's a position vector. R bar of t, I'll define it. So where the particle is initially, say let it be at A. Then after some time, the particle is going to move along the path. It's going to move along the path. So after some time, the particle will arrive here. So that then it will take this position. Okay, then finally, let it be somewhere here. You can choose anything. So it will be, this will be the thing. Okay, look at the position vector. The displacement vector of the particle. So can we show it to be like this? There's a one thing. What are these red color arrows? They are the displacement vectors. So this will be the R1 bar. This will be position vector R1 bar, R2 bar, R3 bar. So particle is at A. After some time, it will be at point P1. After some time, it will be at point P2. After some time, it will be at point P3. So what is this? This is a path. I think, let me start like this. The particle will start at point A. Somebody is asking, what is this? Okay, there's a point A. The particle will start at point A. It will move along this curved path. Okay, fine. So it's going to move along this curved path. Okay, I'll do one thing for your convenient. So what is this blue color line? Is a path of a particle. No. So this particular particle from at t equals it will start at A. When the particle is at A, I'll define its position by a position vector R of t. Then after some time, it'll be at point P1. Then what is the displacement? This will be the displacement vector. This will be the displacement vector. Okay, this distance AP1. So what it should be? It should be the displacement vector. Sir, how you can call that as a displacement vector? Okay, very simple method. If this is the thing that one, so this is R of R bar, you write it. This R1 bar. Particle is at point A. After some time will be available at point P1. So what is the, how is the path? It's going to move in curved path. What is the displacement? The displacement is, so you are going to take this as the displacement. Are you looking at this? So this will become delta R1 bar. Then how we write from the vector addition, R bar plus delta R1 bar equal to R1 bar. So delta R1 bar, what you can write it as? Or delta R1 bar, I can write it as R1 bar minus R1 bar. This is the displacement vector. Very simple, just say like a particle is at A, after some time it will be at point P1. So what is the time? So this I'll write it as T equal to delta T1. After some time, T equal to delta T2, T equal to delta T3. The time interval I'm going to measure from here. In interval of time delta T1, it will be here. In interval of time delta T2, it will be here. In interval of time delta T3, the particle will be at point P3. So in interval of time delta T1, the particle is having a displacement of delta R1. So displacement, so displacement, what is delta R1? We can say magnitude of displacement in interval of time delta T1. That's a basic idea. Then how you define average velocity? Average velocity in time interval delta T1 should be equal to V average 1. Let me write it. V average 1. This should be equal to delta R1 bar by delta T1 bar. And how that average velocity will be directed? In the direction of displacement. In the direction of displacement. Are you getting this one? So therefore, the V average one, I have to show in this one. So here, so we will indicate what are those terms. What is the meaning of that one? So this should be equal to V average 1. What about this another arrow? V average 2. What about this? V average 3. So is it justified to bring that arrow? Okay, getting now. So this should be the V average 1. If you're able to understand this, it'll be very easy for me. Okay, now come for this one. In an interval of time delta T2, how much of displacement the particle is having? Delta R2. One more diagram. Delta R. Okay, now this will be the position vector R bar at point A. This is P2. This is R2 bar. And this is V average 2 bar. And this should be the R2 bar. At T equals 0, it is here. After some time T, the particle is at point P2. This is a path. Distance covered will be like this. This is a path, but the displacement will be in this direction. So again, here the same method, R bar plus delta R2 bar minus R2 bar equal to 0. So delta R2 bar is equal to R2 bar minus R bar. Then what is average velocity? V average 2 should be equal to delta R2 bar by delta T2. So are you getting now? So what is the direction of average velocity? So here I'm going to, as we so if a particle moves in an interval of time delta T1 open, the particle will move from A to P1. Then it will have a displacement delta R1. Then the average velocity V average 1 will be like this. In an interval of time delta T2, the particle what happened will move from A to P2. Then how much of displacement? Delta R2. Agreed. In an interval of time delta T3, the particle how much of path length it will move? A, P1, P2, P3. Then how much of displacement vector? Delta R3. Delta R3, that one. So this P3, let me write it as P now. Let me change it. So this will be much easier. Okay, fine. So what is the let me make it generalized. So this will become the position vector R T bar plus T plus delta T. So in interval of time delta T. So what is it delta T? Time taken by the particle to move from A to P. Then the position vector also will change. Then definitely what happens? This should be the displacement vector AP bar. So the average velocity should be directed in the direction of displacement vector V average. So like this, we'll define it. So what I'm going to do is I'm going to decrease this. I'm going to decrease this time interval delta T from delta T. So from time taken to move from A to P is delta. Time taken to move from A to P2 should be delta T2. I think this time is less. This time is less. Like this, if I keep on decrease this time interval, then what will happen to average velocity vector? Earlier for delta T, look at one more thing, delta T, I'll write it, will be greater than delta T2, greater than delta T1. As I keep on decrease the time interval, during the motion. So what will happen to this average velocity vector? It's keep on going to rotate. It's going to keep on. So now is it displacement vector along the path, along the tangent to the path? Not there. So as I keep on rotate, so as I keep on decrease the delta t, then the displacement vector or the displacement vector will happen. It will start leaning towards the tangent to the path. Okay, somewhere if I make delta t very small, means if the point P, if I bring very close to the A, what do we expect? Somewhere if I bring point here, then the displacement vector will come here. If I make it delta P very small, also like the P delta T very small, such that the point P lies very close to the A. So how the displacement vector will be almost tangential to the path. Will I agree? This one. So what I'm going to do is now I'm going to decrease the time interval. So as I decrease the time interval, then this displacement vector will start rotating like this, the R1, R2 bar, the position vector. Then the displacement vector open will also rotate. Then if the point P lies very close to the A, then how the displacement vector delta R bar will be? The delta R bar will be tangential to the path, and how the average velocity will be tangential to the path. Okay, fine. So here I'm going to bring the one best diagram to explain this concept. So earlier, this was the position vector. The position, okay, this was a green color we took it, no? Okay, this was the position graphic. Yeah, now here I'm going to bring the delta R very close to this one. Then now the position vector will be directed, or select this one. So this will be the R bar. I'm just made delta T very small. Then this will become delta R bar. Okay, and this is a path. Look at delta R bar, how it is. It is along. So what is the direction of average velocity also will be same. So how is V average? It is tangential to the path. So I am going to write one very important sentence. So as we go on reducing the time, reducing the time interval delta T to 0, while doing so, we observe that the displacement vector S bar, I'll write it, which is equal to delta R bar or AP bar. Delta R bar or AP bar gradually leaning towards the tangent drawn at P. So as we know that average velocity, we average points in the direction of V average points in the direction of displacement vector delta r bar. So therefore, hence V average bar will be tangential to the path when delta t tends to 0. This is something very, very important. So finally, what we'll write it as eventually, or finally, better you can write eventually, V average assume say limiting value I think my sentence is correct here, of magnitude and direction, which is known as instantaneous velocity at the point P as shown. Okay, this is the, you can say the the best idea of the best topic of the entire kinematics. Very, very, very difficult and sorry, very, very interesting. A student has to just understand the vector diagram. Nothing big is there. So I'm going to start with this one. What all I just discussed. No. So initially t equals 0, particle is here. After some time t it will be here. So how come you can ask questions, sir? Why delta r bar will be like this? Already I explained. As you keep on decrease the delta t bar interval, so how V average, the V average at one instant for small interval, it will be along the path. Then what is the delta t value? It will be almost tends to 0. Eventually is telling. Almost what happened, the delta t, it will tends to 0. I think I had to show complete description. Yeah. I think you can see the complete. So almost eventually delta t tends to 0. When delta t tends to 0. Okay, fine. So now you have to ask very biggest question. So why delta r? So as at point P, this point P, I'm going to move very close to the A. Then now delta r bar will be tangential to the path. This is the simplest conclusion. Sir, how come you can justify? So I have answer here. You can see this. As the point P moves away from A, the angle between that will keep on increase. You can see this. So if I bring one more here, the angle between that will keep on increase. As the point P moves very close to the angle between the velocity vector and the tangent to the path, it keeps on decreases. So as I move this P very close to the A, or that the time interval delta t, if I tends to 0, then the P will become very close to the A. Then now delta r bar will be tangential to path. And the delta r bar will become displacement vector. And we know average velocity according to definition should be delta r bar by t according to this. So therefore, how the this particular velocity only, I'm going to call it as instantaneous velocity or velocity at that instant. So when average velocity will become instant velocity if delta t tends to 0. So here, so what I'm going to do is like mathematically eventually tends to 0. So therefore here, so we know V average limit of delta t tends to 0. Okay, first we'll define what is V average. What is V average? This should be equal to delta r bar by delta t. So this should be equal to this idea what we have. Then when it will be V average will become instant velocity when limit delta t tends to 0, V average bar will become instantaneous velocity. So limit delta t tends to 0, delta r bar by delta t will become instantaneous velocity. This is further written as dr bar by dt. This is the instant velocity. So how you define instant velocity? It is defined